Okay, so this video is meant to walk you through the equation for induced EMF, and this equation is actually a derivation from a larger equation in looking at the induced magnetic field due to a changing what's called magnetic flux. And a magnetic flux is the amount of magnetic field lines that are traveling through a certain region in space. And we are definitely looking at a simplified version of that bigger equation where here's my induced EMF, symbolized as epsilon. B is the magnetic field in that region. L is the length of the wire that is exposed to the changing magnetic field. And that could be a long wire, that could be a wire that is coiled up. Now V is here, we're really kind of simplifying this, and we're saying this is the velocity of the change. And usually we think of velocity as being meters per second. And definitely we can relate this to meters per second because if we have, for example, if a coil of wire or a wire is physically moving in a given space, we can relate that to like how fast meters per second is changing in terms of if it's the magnetic field that is changing. Usually what's happening with our magnetic field is it is essentially going through like a 360-degree change, and we can interpret that rads per second into almost like meters per second if you think about just the size of the magnet and the extent of which that magnetic field is being exposed to the wire, like where that point is. So this is really where we're oversimplifying this equation. And then theta is just the angle between my magnetic field and my loop of wire. And remember, induced EMF is just a voltage, which is creating this induced current. So remember, the Lenz's law said that my magnetic field is changing. That changing magnetic field creates an electric field. That electric field causes current to flow, and that electric field, the creation of the electric field is what we consider to be the induced EMF, which is causing the current to flow. And that current flowing creates a new magnetic field that opposes the change in the original magnetic field. Okay, so let's just go through the mathematics of this, an example. So this is our equation, induced EMF equals BLV times sine of theta. So this is a 30-meter long, it should say wire. A 30-meter long wire, I should insert that, is coiled up and moves at a rate of 2 meters per second in a perpendicular direction through a 0.5 Tesla magnetic field. What is the induced EMF in the wire? So again, here, let's just identify variables. That's just our good practice. So 30-meter long is our length of wire. 2 meters per second is the relative velocity between our wire and a magnetic field. Our magnetic field that is there is 0.5 Tesla, and we're looking for the induced EMF. So here is our BLV, sine, not in, sine of theta, and we're told that it's perpendicular, so my angle is 90 degrees, and pretty straightforward calculation. So 0.5 times length of 30 times velocity of 2 times sine of 90. Sine of 90 is just 1. So you should actually mental math this. This is just going to be 30 volts. And the second part of the question says, if the wire has resistance of 15 ohms, so that's my R value, what is the induced current? So here I have a voltage and a resistance. How do I find current? That is back to good old Ohm's law. I is equal to V over R, so 30 volts over 15 ohms is a whopping 2 amps. Okay, and then just one more example. At what speed would a 2.5 Tesla magnet, so that's have to move in order to induce a voltage of 10 volts in a 0.2 meter long wire? That's our length. We're looking for the velocity, and it would need to move perpendicular to get a maximum voltage. So that would be part of our answer because it's a velocity. It wants to do magnitude and direction. So here's our equation, BLV sine of theta. So 10 is going to equal to 2.5 times length, which is 0.2. I'm looking for velocity, and I'm saying it to be maximum, I want it to be sine of 90. And so we crunch that out. Again, you could mental math this, but some of you are like, I can't do anything mental at this point. Our velocity is 20 meters per second, and we would say perpendicular to the magnetic field. Okay, so that is just some examples of how to actually calculate induced EMF using our equation.